Hello, everybody. This is Mr. Aklilu Elias, and today I'm going to present my third seminar topic, that is what we say LLM efficiency, reasoning, and multimodal integration. And uh, uh, I would like to say you welcome back. In the previous seminar sessions, I presented the neurosymbolic AI and a knowledge graph in the first seminar session. And in the next seminar, also, I presented the world models and grounded reasoning. And you have got a lot of informations that are very important on that seminar sessions. Today also, I would like to thank all of you for giving time to attend my third seminar session, and it is just presented for Professor D.P. Sharma, who is our PhD program coordinator in Arvamink University, Arvamink Institute of Technology, Faculty of Computing and Software Engineering, and PhD in Computing and Information Technology specialization. And I am also specializing in this program in the computational linguistics. And today seminar topic is what we say large language model efficiency, reasoning, and multimodal integrations. And in this seminar topic, there are a lot of topics that are covered. The first one is overall diagram of the seminar or the topic, and the second one is overview, that I am going to give you the overall overview about the seminar, and the third one is introduction, which deals about this topic, and another one is most important thing that describes about the components of large language models, and the third one is the convergence technology of these things, and the fourth one is integration and innovation and training paradigms and data sets, advantages and disadvantages of LLM components, and the key methodological innovations, applications across this domain, and future research directions in multimodal LLM integrations. And finally, I am going to give you the overall conclusion about the seminar. And again, lastly, there are some research topics that are that will be addressed or that are discussed regarding to this seminar topic that can be conducted as a PhD dissertation, or it can also be conducted as a master's thesis, and for another kind of research and community service activities. And finally, there are references. So while I come to the first part of this seminar, there is here I am going to present the diagram which deals about the entire seminar. The first one is LLM efficiency. This is the first component. Totally, the overall seminar, this seminar topic can be categorized into three components. The first component deals about the LLM efficiency. The second component deals about LLM reasoning. And the third component deals about multimodal integration or interaction. So while I come to the first one, here the LLM efficiency, here the term efficiency is to measure how well an LLM uses resources to produce accurate results. So here efficiency comes together with accurate result or producing accurate result. And this efficiency is useful for generating faster response time, and it is also useful for lower compute costing. It is for the better memory usage, and it is for the scalable performance. This thing deals about the efficiency of large language models. And finally, the goal of this efficiency is just to get best results with a minimum time, cost, and resources. And the first component deals about all these things. And while I come to the second component, it is all about large language model, a reasoning component. Here, it is all about reasoning component. So here, the reasoning is what we say, the ability of large language models to think, to understand, to solve problems. That is what we say, a reasoning skill. So in this part, it has LLM must be able to think things, to understand the things, and to solve a problem is one by one. And to do this, it must understand the context of the things that is given for it, and within that, it logically thinks, and again, it solves the problems step by step by reasoning, and finally, it handles the complex problems. So this component has an important goal, which is to make accurate decisions and solve complex tasks. This is the goal of LLM reasoning component. And the third one is multimodal interaction component, or we can say multimodal integration component. And in this part, since the term is considered as multimodal, that deals about multiple kinds of input data sets. For example, text can be considered as one data set, image can be another kind of data, audio or speech can be considered as another kind of data, and video can be considered as another kind of data. We can also add here animations, and again, we can here add graphics as an input data set. And all these data sets merge together or combine together or interacted together to form multimodality. And here it deals about multimodal interaction. So LLM can understand and interact using multiple types of inputs and outputs. And the final goal for it is that to communicate and understand the world like humans understand. This is what we say, the multimodal interaction session. So these three components can be interacted together. Therefore, we can build efficient LLM that can reason and that can integrate, that can generate an output by taking different kinds of data sets or integrated data sets and input, and reasonably think upon that data sets, and again think things among that data sets step by step, and finally solve a given problem like human beings solve a problem. This is all about this seminar session that this diagram deals about. And sorry, the second session is overview. Here I am going to give you the overall overview of this seminar. So here LLM efficiency, reasoning, and multimodal integrations are the three core pillars of modern artificial intelligence developments. So the modern artificial intelligence deals about the efficiency of LLM, the reasoning capacity of LLM, and the multimodal integration mechanism, or the ability of taking multimodal datasets as an input, as an important thing. And these three things can be combined together. And finally, a good AI systems that thinks like humans, performs tasks like humans, and solves problems like humans with intelligent behavior can be developed. And they dictate how fast and cheap a model runs, which is all about efficiency, and how it solves complex and multi-step problems. That is what we say reasoning, and how it processes different types of media like images, video, audio, is what we say multimodal integrations. And these three components are described one in detail in the next slides. So it is all about this multimodal integration. So here multimodal LLMs are class of models that extend LLMs to process, to align, reason over data from multiple modalities, including text, image, audio, video, serious, and structured informations. So this model is built upon a core strengths of natural language processing, LLMs, by incorporating specialized encoders, alignment and fusion mechanisms, and cross-modal training objectives, enabling wide range of new applications that require integrated understanding and generation across diverse data types. So let me come to the introduction session that contemporary NLP seminar topics focus on LLM efficiency, reasoning, and multimodal integration. So here the core domain of these models extends far beyond the text mapping inputs to structured data actions, codes, or images. Rather, this theme is perfectly suited advanced cutting-edge seminar discussions. And multimodal LLMs are advanced AI systems that integrate and process diverse data types, text, image, audio, video for unified reasoning. They utilize specialized modality encoders, alignment modules, and cross-attention mechanisms to efficiently fuse multimodal information. And applications span vision language tasks, scientific reasoning, and real-time data integration, driving innovation in both research and industry. This is all about the introduction part. So let me come to the components of this LLM session. The first component is efficiency component. Efficiency component, what I discussed in the first session in the given diagram. So here LLM efficiency refers to techniques that focus on reducing the computational power, memory, electricity, time required to train and deploy artificial models. So while we talking about efficiency, we are dealing about just reducing computational power. We are dealing about saving memory. We are dealing about electricity consumption, and we are dealing about time saving, which is required to train and deploy artificial intelligent models. Since massive models are historically expensive to host, efficiency makes them faster, cheaper to operate, and deployable on smaller devices like phones or edge servers. As model grows larger, making them efficient ensures that they can run quickly on affordably on cloud servers or directly on consumer hardware like smartphones. So the overall goal of LLM efficiency is to maximize accuracy and minimize latency, cost, and hardware requirements. And the efficiency component has different kinds of techniques that we can make LLM components very efficient. To make the LLM component efficient, we can use techniques like quantization. We can use a technique like mixture of experts. We can use another technique like pruning, and we can also use another technique like KB catching and token compressions. So these techniques, all of these techniques have their own advantages for the LLM efficiency. So while we come to quantization part here, quantization, it deals about compressing a model by converting its numerical weights from high precision formats like 16-bit to lower precision formats like 8-bit or 4 bits to dramatically save a memory. And the second technique is what we say mixture of experts. Here, routing is specific queries, specialized sub-networks or experts inside a model rather than activating the entire neural network for every single prompt. So here, it is a mechanism of selectively activating a required neural model component to run a given task, meaning that if a task needs a specialized neural component to be activated, it only activates that component only, rather while keeping all other components in a silent or in a sleep mode. And if in a neural network model, if a task needs to be activated with another component. Again, this technology activates the only required component to be activated, rather keeping all remaining components in a sleep mode. And this technology is what we say a mixture of experts. And the third technique that helps for making LLM efficient is what we say pruning. So this technique is a mechanism of discarding unnecessary or redundant connections within the neural network that do not heavily contribute to the output quality, meaning that if there is any neural component that has no advantage for generating a qualified data, that special component becomes pruned out from the model. This is what we say pruning. So we remove unnecessary components from the model and we only keep required or very important component that is useful for making the output in a very good quality. And this technology or this technique is what we say pruning. And the fourth technique is what we say KV caching and token compression. Here we are dealing all about compression, which is storing previous conversational steps or compressing intermediate reasoning steps into shorter mechanical forms to avoid redundant recalculations. These are the techniques that helps LLM to be efficient. And the second component is what we say a reasoning component, as we have seen from the diagram. It refers to a model ability to execute a structured multi-step logical thinking rather than just predicting the next most likely world. So here it is critical for solving highly complex problems in math, computer coding, science, and in logic. So here reasoning is the ability of large language models to go beyond simple pattern matching and perform step-by-step logical deduction, planning, and problem solving. And it has also its own mechanisms and its own techniques. So here, one of the mechanism is just advanced models often use chain of thoughts or what we say COT prompting to break down complex problems into smaller problems. So here, the modern reasoning focused on architectures employ reinforcement learning to think, that is, generate hidden internal tokens before writing out their final answer. And the goal of reasoning component, as we have seen before, is that allow models to self-correct or correcting itself by itself and debugging the code, just that is what we say, checking whether the code is correct or not, and solve advances mathematical calculations and make autonomous decisions without hallucinating or without making any hallucination. So here the goal is just the model performs and performs each and every task by its own. It reasons, it checks the things by itself and performs or gives a required decision. That is what we say the autonomous behavior of the model's reasoning component. And this component has their own techniques that helps a component to reason in a required or an enough mechanism. So to make a model to reason in enough manner or required manner, we can use technologies like chain of thought, what we say COT, inference time compute scaling, and reinforcement learning mechanisms. So this thing helps the model to reason in required manner. So the first one, what we say chain of thought or COT, is what a mechanism of prompting or training a model to break down a single massive problem into a sequence of smaller variable intermediate steps before producing a final answer. In this case, if the given step is very long, this technology or this technique breaks down the long steps into some smaller steps or some smaller sub-steps. and then each and every steps performs their own or their assigned task and finally generate the final answer. And this is what we say a chain of thought technique. And the second one is inference time compute scaling. Here, giving the model extra time to think before answering. That is as seen in advanced architectures like OpenAI or DeepSeek R1. The model generates hidden inner monologues to double-check its own logic and fix its own mistakes. So here, the most important thing is that giving the model extra time to think things before generating an output. And by doing so, it corrects its mistakes by its own. This is what we say inference time compute scaling technique. And the third one is reinforcement learning. That is just a mechanism of rewarding a model if it performs a given task in correct manner and punishing a model if it makes a mistake while performing a given task. That is the same with what we know about reinforcement learning in the machine learning courses. So a reinforcement training models using reward systems based on mathematical accuracy, meaning that if the thing is calculated correctly or performed correctly, or code execution feedback to discover the best logical paths through trial and error mechanisms. By this mechanism, the model trains by itself, by rewarding itself for the correct actions and by punishing itself for wrong actions. And this is the third most important technique that makes LLM to be good reasoning AI. And the third component is what we say multimodal integration component. Here we mostly talk about is multimodality. Multimodality, these are just input data in a multiple forms that are integrated together to form a multimodal component, which is the third component of the diagram what we have seen so far. So multimodal integration is the process of expanding LLM architectures so it can seamlessly process, align, and generate data across different sensory formats such as text, image, audio, video, and code. So here it allows a text based on LLM to process, understand, and generate multiple types of data. What is with which we say multiple data modalities simultaneously, such as text, image, audio, video, sensory input data, and another kinds of data types. And these data types are integrated together to say them as multimodality, and they are integrated together and form the third component, which is very important for LLM. And the mechanism is just instead of separate specialized models for text, vision, these systems use projection layers like encoders that translate raw visual or audio data into LLM's internal language spaces. The most important thing we have to understand about this component is that rather than creating a separate model for a text, another separate model for audio, another separate model for video, and another separate model for other kinds of data sets, it is possible to integrate all these input data types such as audio, video, and other kinds of data sets, for example, animation and graphics. All this data can be combined or converged together as a single data to create multimodality, and this multimodal data can be given as an input for a model. Then finally that input can be processed and LLM with good performance can be generated that can surely perform things like humans do in the real environment. And the final goal of this multimodal integration component is just for creating unified AI agent which is capable of perceiving the environment, interacting the environment in the real world. For example, describing an image or analyzing a video just as humans do. This is what we say. Human things can just perceive the environment, and humans give a feedback according to the environment. And humans perceive the environment, and humans act upon the environment according to the perceived information they get from the environment. And that makes human beings to be more intelligent in than all kinds of animals that are living in the world. So the goal of just multimodal integration is creating AI systems or AI agents that can do tasks just like humans do in the real environment. This is all about multimodal integration component. And to make this, we can use various kinds of techniques. The first technique is cross-modal alignment technique. The second technique is modality encoders and projections technique. And the third one is omni-capable interaction technique. What about the cross-modal alignment technique focus? Here, it is a mechanism of fusing different inputs so the model understands the direct relationships between them. For example, we have to match the spoken word dog in a text with an audio file with a physical dog in picture or in a video. That is what we say modal alignments. While we say dog, the model must align it with a dog in video or a dog in a real world. That is what we say multimodal alignment. And the second one is modality encoders and projectors. Here we are just using specialized tools like vision transformers to convert visual data into tokens that the central language model can read and process alongside with a text. This is modality encoders and the projections. And the third technique is all about omni-capable interaction. Omni-capable interaction here, it is allowing users to interact using mixed inputs and outputs. For instance, you can upload a blueprint image, ask a voice question about it, and receive a newly generated chart or text summary as a response, and which is for omni-capable interaction mechanisms. And it is all about the techniques that we can use for multimodal integration. And it is all about the convergence technology, which is combination of different kinds of technologies together. That is what we say it as convergence technology. For example, we can combine a multiple kinds of machine learning models with another kind of deep learning models, and the combined effect becomes convergence of the models. And we can also combine sequence to sequence models with attention-based transformer models together, and finally we can get combined models, which is what we say the convergence technology. So here, this technology deals about the efficient combination of these three components together in effectively functional way. How they connect together? Here, the true state of the art in AI lies at the interaction or the intersection of all these three components together in a fully or a well-functioning manner. So, to build an efficient multimodal reasoning model, developers must teach AI tools to look at a complex video, that is what we say multimodality, and think systematically through step-by-step physics problem hidden with that video, which is what we say a reasoning. And the third one is do so fast enough to run seamlessly on a personal laptop or smartphones, which is what we say efficiency. So by combining efficiency with multimodal reasoning capacity, it is possible to create AI systems that can do things like humans do in the real world. So the current frontiers or boundary or the scope of AI combines all these three technologies together. So developers are actively dealing or building models that can process video or images That is what we say multimodality, think through them logically without making things up, which is what we say reasoning, and while keeping the process fast enough to use in real time, which is what we say efficiency together, and which is just all that is the basic thing, which what I am discussing in this seminar session. So supported by high quality data, scalable infrastructures, safety mechanisms, and the evaluation frameworks, these three pillars combine together to create powerful artificial intelligence systems or agents that are capable of serving a wide range of real-world applications like humans do. So, multimodal large language models, integration and innovation technologies are all about what I mentioned here. So, multimodal LLMs are advanced AI systems that integrate and process diverse data types. For example, text, image, audio, and video for unified reasoning. And they utilize specialized modality encoders, alignment modules, and cross-attention mechanisms to efficiently fuse multimodal information. And applications span vision language tasks, scientific reasoning, and real-time data integration, driving innovation in both research and industry. And the multimodal LLMs architectures are typically structured with 3 to 5 interacting components. For example, the first component deals about modality encoders. Here, each supported modality, for example, video, audio, text, video, is passed through dedicated encoders such as clip, visual transformer for images, whisper for audio, 1D ResNet for time series, or BERT for tabular data to produce a learned feature representations. And input projection model or component, or we can say alignment component or module, here to reconcile differing latent spaces. Encoders outputs are transformed, for example, with linear layers, one-dimension convolutions, crossed attention blocks, or projectors, so they align with the token embedding space used by the LLM backbone. And another component is LLM backbone, what is considered as cognitive module. Here, the central LLM incorporates both text and aligned modality soft tokens into an integrated input sequence, and this leverage pre-trained strings in language reasoning and generalizations while extending to multimodal tasks. And output projection or modality generator for output in non-text modalities, output tokens are mapped to the required modality space, for example, serving as input latent diffusion models for image or audio systems. And the last one is specialized memory or expert modules. So here, some advanced models like MKS2 augment or replace the standard LLM blocks with modular visual memory or mixtures of multimodal experts structures, allowing the model to store and recall modality-specific knowledge for reasoning generations. So integration strategies range from a simple token concatenation to cross-attention layers to plug and apply temporal modules for videos and to composite attention mechanisms for compute efficiency. So what are the training paradigms and the data sets that are useful to create this kind of AI system? Here, multimodal LLMs are rely on 2 key training strategies while we deal about data set paradigms. The first one is multimodal pre-training. Here, the models are initially trained on large-scale modality text paired datasets. For example, image is aligned with a text. Here, this text must deal about the aligned image. The second one is the video with a text. Here also, this text deals about attached video together, And the third one is audio with a text. So this text deals about attached video together. That is what we say multimodal pre-training alignment mechanism. And here pre-training objectives often combine text, token prediction, constructive alignment, and mean square error between projected signals and modality targets. Hard negative mining is used to prevent modality bias in retrieval tasks. Here we can use hard negative mining technique to prevent modality bias in a retrieval mechanism, and some scholars mentioned about this issue. And here multimodal instruction tuning is the first paradigm, which is related with data sets. Here, to enable versatile instruction following behaviors, a second stage of fine-tuning is performed using data formatted as dialogue or tasks. So this enables models to respond to natural instructions and multi-turn contexts. And lastly, we can see high quality, diverse datasets drive performance more than scale-alone datasets, include both supervision and synthetic instruction response pairs. And this is all about training paradigms regarding to data sets in LLM efficiency and reasoning with multimodality. And this technology has also its own advantage and disadvantage. So we can separately look the advantages and disadvantages in the component wise. And the first component is efficiency. In this efficiency component, there are advantages. The first one is it lower a cost. It is very accessible, and accessibility is another advantage. And the third one is saving or keeping time, saving time that is related with speed. So lower cost is reduced computational power translates directly to cheaper API calls and less expensive local hardware maintenance instead. That is one advantage. In related to accessibility, smaller models like quantized or pruned versions can run on edge devices like smartphones without needing cloud connectivity. And the third one is speed. Lower latency allows for real-time applications such as live translation or rapid customer support chatbots. And disadvantage of efficiency component is that capacity loss and diminish the returns. So a capacity loss deals about compressing models or using fewer parameters can decrease their broad knowledge base and nuanced understanding. And the second disadvantage of the efficiency component is that diminished the returns, meaning that pushing for maximum efficiency often requires complex fine-tuning. For example, knowledge distillation that risks degrading overall quality output for the efficiency component. And the second component is what we say reasoning component, and it has also its own advantage and a disadvantage. There are three advantages for this component. The first one is better complex problem solving. Here, it drastically improves performance in mathematics, in logic, and abstract reasoning tasks. That is one advantage. The second one is it can correct error by itself. So here, error correction allows the model to evaluate intermediate steps and course correct before providing a final answer, reducing different kinds of hallucinations. And the third advantage is handling unseen scenarios. Here, it enables models to adapt to novel situations rather than simply pattern matching training data. And the reasoning component has also disadvantages. The first one is it is slower response time, meaning that multi-step reasoning and self-reflection requires significantly more processing time per query. And another disadvantage is that it needs higher compute cost, meaning that generating internal thought and verifying steps consuming more tokens and computational resource driving up operating costs. And The third component is also what we say multimodal integration component, and this component has also its own advantage and disadvantage. The first one is advantage session here. Holistic understanding is one advantage. Models can grasp the full context of situation by analyzing diverse inputs together. For example, reading the text on a diagram while analyzing the image is one of its advantage as holistic understanding. The second advantage is what we say user versatility, meaning that it opens intuitive use case like real-time visual translation, image generation from text or audio to text transcriptions. That is what is we say user versatility. And the last advantage is a rich output, meaning that it generates a diverse media types, making interactions feel more natural and dynamic than than humans do. And the outputs are very rich, which is just can be similar with that of human beings do, which is another advantage. And also it has a disadvantage, meaning that the first disadvantage is architectural complexity, meaning that the overall architecture is complex, and managing different data modalities requires massive, highly complex architectures that are difficult and expensive to train. And another disadvantage is privacy and safety risk, meaning that processing live visual and audio data introduces complex data privacy concerns and potential exposure to sensitive generations or information generations. This is what we say these are one for the sensitive information. Since information is sensitive, it must be kept secret. So there is a privacy and a safety risks problem as a disadvantage in the multimodal integration component. And we can see the key methodological innovations in this technology, and it deals about several generations, alignment, and reasoning techniques that support multimodal LLM performance. As a composite and cross attention, stepwise reasoning and chain of thought methodological innovation, and another one is plug and apply temporal modules, memory and knowledge storage, universal retrieval and re-ranking, and hybrid graph integrations are related with the key methodological innovations of this particular technology. And it can be applied in various domains across different perspectives. For example, the versatility of multimodal LLM is reflected in their diverse real-world use cases. For example, it can be applied in visual language integration for tasks include image captioning, visual question answering, chart and document understanding. And again, it can be applied in the video and audio understanding, like video LLMs support video question and answering, action recognition, scan description, and dynamic content understanding. And again, it can be applied in the health and the medicine industry. It can be applied in the science and reasoning. It can be applied in retrieval and editing and generation. And again, it can be applied in human-centric interfaces. And these are the application domains of this technology. So, what are the future research directions of this technology? So, research in multimodal LLMs continues to advance along several promising boundaries. The first one is research can be conducted in embodied and continual learning. Here, this one is just moving beyond static data sets to embodied and integrative setting. For example, robotics, real-time agents, sensor fusion for intelligent transformations, and towards continual learning without catastrophic forgetting mechanisms can be considered as one of the most important research paradigm of this technology. And another one is generalized and efficient architecture development. Here, developing unified backbones supporting more modalities, for example, time series, structured tables, multimodal graphs, resource-efficient adaptations, composite or training-free modules, and expert mixing strategies are another most important research domains in generalized and efficient architectural developments. And another kind of research domain is safety and robustness. Here, enhanced method for detection and defense against cross-modal adversarial attacks, addressing ethical risks through better monitoring, alignment, and interpretability mechanism is the most important research domain, which needs also critical attention for this technology. Again, structured reasoning is another research direction or domain of this technology. For example, integrating more transparent and interpretable multi-step reasoning frameworks, especially for tasks requiring chained or tree-structured logic beyond simple language output, is very important research direction, which motivates different kinds of scholars and researchers in this domain. And again, there is open source and ecosystem and benchmarking research domain that needs curation of high quality, diverse, and challenging benchmarks. For example, SimVecBis, SciQA, MBERT datasets, and open tools for collaborative tracking and evaluation remains a major focus for a community-driven progress for researchers in this domain. So scholars and scientists can develop or focus on these particular areas to develop multimodal LLM that focus about embodied and continual learning that is related with developing generalized and efficient architectures, which focuses on the safety and the robustness of LLM, and again, which focuses on structured reasoning mechanism and just developing a system which is open source ecosystem and benchmarking for these different kinds of domains to be applied. These are the most important research domains or the current research or the contemporary research domains of this technology. And finally, the conclusion for this seminar is that this mechanism we can create by doing so, by using the aforementioned mechanisms, it is possible to create artificial intelligence systems with efficiency, with reasoning power and multimodal capability that makes it more capable, reliable, and useful. Meaning that, in short, efficiency for LLM deals about the model's practical behavior. Reasoning makes the model intelligent enough. Multimodality makes the models versatile, and together it is possible to create a next generation AI system that can just replace or that can do things like human beings does in the real environment. And this is all about this seminar session. And again, here I have mentioned some research topics that can be conducted in our context. For example, in the language context in Ethiopia, there are different kinds of languages. More than 80 languages are spoken in Ethiopia, and most of the Ethiopian languages are unresearched and they suffered with data scarcities. So it is possible to create multimodal data integration and linguistically localized English Walaita neural machine translation using transformer architectures and another convergence technologies. So here I mentioned for English Walaita machine translation. So this research can be conducted for other kind of languages. And here it can also be conducted for bidirectional English Walaita. And in the place of Walaita language, it is possible to put other kinds of Ethiopian languages or another less researched and less developed African languages, such as Amharic language, Oromifa, and Afan Sidamu, and Afan Afar, and Afan Somali, and again, Gamo and Gopa and Dauro languages can be conducted with this topic. And again, it is also possible to converge multimodal, data-oriented, and context-aware conversational AI for various kinds of Ethiopian languages. So here, what matters is convergence of different technologies that uses multimodal data sets together as an input. And again, the system finally will be generated must be the context-aware system that understands the community perspective. And finally, the cumulative effect becomes conversational AI for a certain kind of language, such as Walaita language. So here, the parameters, convergence is most important thing, multimodality is another important thing, and here, context awareness is also most important parameter. Here, conversational AI is considered as one key term. And lastly, this is a language which needs convergence, multimodal data integration, context awareness, and can be considered as AI system that community can use in the real environment. And these are the research topics mentioned regarding to this seminar topic. And finally, here are references I have used to get most important contents or information about these data sets. And this is all about my seminar presentation. And if you have any question or comment or suggestion, you are welcome. And you can contact me through my email, which is mentioned in the first part of this report or presentation. And again, you can also contact me through the various social media systems. For example, you can contact me through Twitter, you can contact me through uh, WhatsApp, and again, you can contact me Telegram or Facebook. By any formality, it is possible to contact me if you have any question or suggestion or comment or clarity regarding to all the three seminar topics that are mentioned so far. For example, neurosymbolic AI and the knowledge graph, world models and the grounded reasoning, and the third one is LLM efficiency, reasoning, and multimodality. These three seminars are covered by me, and anybody with question can catch me through contact me through the aforementioned informations. Goodbye. Thank you very much. See you.